Hello guys, welcome to watch our video. As you see, our lesson is talking about the continuity and the differentiability. Before I begin to explain this lesson, I have to remind you how we find the derivative at a point. Okay? Look here. If this function, as you see, f of x, as you see, it's a curve in yellow color. It is continuous at x equals c, continuous, okay? I'd like to find the derivative at this point. As you know, the derivative at any point, it means at any point on the curve of the function f of x, it means the slope of tangent, as you see, which in green color, as you see here. The slope of this tangent, it means the derivative. Okay, how to find the slope of the tangent at the point x equals c? As you see here, if we have another point, for any point x, as you know, the secant, it is a line which intersects with the curve of the function at 2 points. As x approaches to c, f of x approaches to the f of c. In this case, this point approaches to this point, and the secant approaches to the tangent. How we get this one? As you know, this one, x minus c. This one, it means f of x minus f of c. The slope of the secant, it will be the rise over run. As this, as x approaches c, so the slope of the secant approaches to the slope of the tangent. I'd like to remind you that is alternative form of the derivative of function at a point, which means slope of the tangent at this point. I just remind you because I explained this one before in the first session. Please watch the videos, the first video again. Look here. I'd like to define when the function differentiable at a point, or the differentiability at a point. F of x is differentiable, okay, at point x equals c if it is satisfied two conditions. The first one, continuous. If the function not continuous, it will not be differentiable. The second one, as you know, the derivative exists, the derivative at the point x equals c exists if this limit exists. This limit exists if the limit from right as the limit from left. Here, limit from right, it means the derivative from right. The derivative from right. Right hand derivative equal what? Left hand derivative. Understand? Right-handed derivative, it means this one, limit f of x minus f of c over x minus c over c from right. Understand? That is the meaning right-handed derivative. Right-hand derivative. Okay, but means here, look with me, left-handed derivative, it means this limit when x approaches to c from left. This limit, as you see in green color, when approaches to c from left. Okay, two conditions must be satisfied. Any one of them fail, so the function is not differentiable. Okay, from here you have to know, please, it is enough if the function continuous, it is differentiable. No, it must satisfy the second condition. I'd like to tell you, if the function, okay, not continuous, this one implies it is not differentiable. Understand? If it is not continuous. Okay, if the function continuous. This implies too it will be differentiable, not enough to be differentiable. Not enough to be differentiable because it must satisfy these two conditions. Left-hand derivative equals the right-hand derivative. But I'd like to tell you, if the function differentiable, it means it satisfies two conditions. It is continuous and left-hand derivative equals the right-hand derivative. Okay? So, I'd like to say if the function differentiable, this implies it is what? Continuous. If the function differentiable, it is continuous and the right-hand derivative equals the left-hand derivative. So differentiability implies to continuity, but the continuity not enough to implies to what? Differentiable. Okay, differentiability. Means here. Let's discuss together this one. Some functions. Look here. Differentiability on an open interval, it means the function differentiable at every point on this interval or in this interval. The function differentiable overall, if it is what? Differentiable at every point in its domain, Look here. Differentiability of a function at a point, it means how the curve is smooth. How the curve is what? Smooth. Understand? There is no sharp point, as I'll show you here in this one. Focus with me to understand everything. If we have a function in this shape, that is our function f of x. Okay? I'd like to discuss the continuity at this function at the point C. As you see, the function is what? Continuous because it has no interruption. What is the mean interruption? Hole, gap, vertical asymptote, okay? Or jump. It is continuous. This function f of x is what? Continuous. Is continuous, okay? About the differentiability. The first, it must satisfy two conditions. The first one is satisfy. What is the second one? Left-hand derivative at the right-hand derivative. Left-hand derivative, it means the slope of the tangent at its right. Look here, at the left, that is the tangent to this point, to the curve of the function, at the point C from left. Okay? The slope of this tangent, it means what? The left-hand derivative, because the derivative is a slope of tangent. Okay? From the right, that is the slope of this tangent at the right of the point C, the slope of the tangent to the curve of the function f of x at the right of C. Equal what? Right-hand derivative. As you see, we have different tangent lines. In this case, so left-hand derivative not equal the right-hand derivative. Left-hand derivative not equal right-hand derivative. Okay? In this case, f of x is not differentiable. Okay? At x equals c. I'd like to make you understand the concept. What is the meaning of left-hand derivative, right-hand derivative? Our lesson today finds the relationship between continuity and differentiability graphically, analytically later. Okay? Look here with me. As you see, the function, one of the two conditions that must be satisfied, such as the function differentiable at a given point, is filled, which is the left-hand derivative not equal the right-hand derivative. Okay? I name this point, we name, look here, this point at which, like this case, we name it sharp point. At the sharp point if the curve of the function has a sharp point, at this sharp point the function not differentiable. That is the first case. Sharp point at which the function not differentiable. Okay. Second case I'd like to discuss with you. Second case, if we have like this curve. Okay. At this point, for example, A, is the function continuous? Yes, it's so clear. Continuity, it means there is no interruption has been done in the curve of the function. So, function f of x is continuous. I refer to continuity by using C for you, okay, to save the time of writing. Is the function differentiable? The first condition is satisfied, is continuous. But find the derivative at the left, okay, that is the slope of tangent. The slope of this tangent, it means left hand derivative. Okay, find the slope of the tangent at the right. It has different tangent lines from right and from left. Slope of this tangent equal what? Right hand derivative. So this function is not differentiable because the second condition is not satisfied. F of x is not differentiable. Okay? Understand or no? Yes. Please wait just 1 minute. So, as you see, the function is not differentiable because it is not satisfied the second condition. Not satisfied the second condition. Okay? At this point, in this shape of the curve of the function, as you see, as a line here and a curve here, we name it, it has what? Cusp. Okay? Cusp, like this shape. Sharp point as in absolute function, okay, like this one, not differentiable, that is sharp. What do we mean by sharp, which has like this shape, okay? I have up to now 2 cases. Sharp point function is not differentiable, cusp, it is not differentiable. Let's see another shape or another curve of function which is not differentiable at this point, not differentiable at a point. Okay, third shape. Look here. If we have like this one as a point, for example, A, the curve, it has hole. It has what? Hole. Is this function continuous? This function is not continuous because the curve of the function has been interrupted, as you see. Here, f is not continuous. Why? Because the curve has interrupted, or by another way, it has hole. Since the function not continuous, one of the 2 conditions must be satisfied to be differentiable is what? Failed. That is the most important condition. So f is not differentiable. Here, differentiable. Why the function is not differentiable? Because it is not continuous. Not continuous implies not differentiable. Why? It has hole. It has what? Hole. At hole function not differentiable, not continuous. At the values of point at which we have cusp, as in your teeth, the function is not differentiable. Okay. Let's discuss another shape. Here, if at any point, for example, C, any point, we have what? Jump. As you see, we have what? Jump. Since we have jump, f is, as we learned before, is not continuous. Understand? Since the function not continuous, so f is not differentiable. Is not what? Differentiable. Since the function not continuous, so it is not differentiable. At jump, this case, because it has what? Jump. Okay? Let's discuss another case. If the function not continuous, it is not differentiable. Okay? Look here. Oh, I'm sorry. For the fifth case, as you see here, if we have at a point vertical asymptote, it means the function undefined at this value, f is not continuous. Okay, since it is not continuous, so f is not differentiable. It is not what? Differentiable. It has what? Vertical asymptote. Okay, vertical what? Asymptote. Okay, the fifth case, number 6. You have to understand. If the function, look here, it has gap. It's what? Gap. It is not continuous because continuity, it means has no interruption. Here, f is not continuous, so f is not differentiable. Not continuous implies do not differentiable, sorry, D. Okay? I hope you understand. I hope you understand. Let's wait. Okay, let's see continuous. Here, as I told you, f is not continuous, so f is not differentiable. Okay? If the function not continuous, okay, graphical, here I'm talking about the continuity and differentiability graphically, not analytically. Later I will show you analytically. I think the last case I show you, it will be, look with me, number 7. If you have a curve of function like this one, like what? This one. At this point A, we have what? Vertical what? Sorry. I like to, yes, wait a minute to show it to you well. Here, look. At this point A, we have what? Vertical tangent. We have vertical tangent. Okay, vertical tangent. As you know, the slope of the vertical tangent is undefined. In this case, we can write what? As you know, f is continuous because there is no interruption. But f is not differentiable. Why? Because it has a vertical tangent and the slope of this tangent undefined. Because it has what? Vertical tangent. Okay? All of these cases at which the function is not differentiable. Because as you know, the differentiability means how is the curve smooth. How is the curve what? Smooth. There is no sharp point. Look with me again. Look here. Oh, I'm sorry. Sorry. Sorry, this one. Wait. Wait, I'm sorry. Look with me here. Okay. I'd like to revise you the all cases at which the function is not. At sharp point, as you see here, in absolute function like this one, sharp point function is not differentiable. At cusp, shape is called cusp. It's called what? Cusp, as in your teeth. This one which has whole jump, vertical asymptote, or have a gap, it means the function not continuous. If the function not continuous, it is not differentiable, as you learned it before in the first term. When the curve, okay, not continuous at any given point at all, a jump, at vertical asymptote, at gap, okay, at this point, at the point which has a vertical tangent, the function is not differentiable. After I explained all of this one, I'd like to show you. Wait, focus with me. I give you enough time. Wait a minute. Yes. This one, as I defined before, differentiability at a point function is differentiable at a point if its derivative exists, as I showed you the definition. Okay, left-hand derivative equal right-hand derivative, and the function continuous. First, continuous. Differentiable on a point, on an interval, if only if and only if it is differentiable for every value on the interval. Differentiability function is differentiable overall if and only if it is differentiable at every point in each domain. Please study well the definition. Look with me here. As I explained before, differentiability implies to continuity, not continuity, not continuous. Continuity implies to differentiability, no, because it must satisfy another condition. Not continuous, it means not differentiable. Look here, I know all of you know how to solve this one. Please pause the video and solve all of this exercise for the student who didn't attend this session. Okay, then play the video again to correct yourself. Example, determine whether the following functions are continuous, differentiable, neither or both at the given point. Here, as you see, at the point 3, I have what? Jump. We have jump. So, since we have jump, the function is not continuous, so it is what? Not differentiable. Okay, please focus. Since the function not continuous, it is what? Not differentiable, so I will write what? Neither. Neither. Why, miss? As you know, it is not continuous, not differentiable, neither. Okay? Because what? We have jump. We have jump. Here, as you see, the function is not continuous, so it is what? Not differentiable. Understand? So we write what? Neither. Okay? Because it has what? Whole. Here, as you see, it is continuous. And if we draw a tangent, it has a tangent, only one tangent. Okay? Its slope 0. As you see, since we have only one tangent, so the left-hand derivative as the right-hand derivative, which is here 0. In this case, we write both. Both. Okay? Because it is continuous and left-hand derivative equal the right-hand derivative, it means the slope of the tangent at the right as the slope of the tangent at the left. Here it's so clear that is the shape of cusp, but that is cusp. One is straight and one curve. That is what? The shape of the cusp. It is continuous, yes, because I don't have any interruption. There is no hole, there is no gap, there is no vertical asymptote, there is no jump. Continuous. Okay, it is what? Continuous. But it is not differentiable because, as you see, as I explained before, the derivative from left, the tangent from left, not as the tangent from right. So the slope, the left-hand derivative, not like the right-hand derivative. It is continuous only. In this case, I have an interruption has been done in the curve. It's so clear because we have a vertical asymptote. We have what? Vertical asymptote. This function, not continuous. Since it is not continuous, it is what? Not differentiable. Here, neither. It is what? Neither. For this point, I know it is continuous, but I have a sharp point here. Vertical asymptote. Okay, but here, why it is not differential? Cusp. I forgot to write cusp. Here we have what? It is continuous, okay? But it is not differentiable because we have what? Sharp point. This one, it's so clear, continuous only. Why? Because there is any interruption has been done in the curve. But we have this shape of what? Cusp. Why it is only? Because it is what? Cusp, okay? Here at this point, because I talk about the given point in the curve, it has vertical tangent. It is continuous only. Why it is only continuous? Because it has what? Vertical tangent. It has what? Vertical what? Tangent. Okay, I hope you understand our lesson. Please, you have to study well. When the function is not differentiable at a sharp point, cusp, at vertical asymptote, at vertical tangent, hole, gap, or what else? Hole, gap, jump. Okay, thank you.